I'm not able to. I have opened my PPT, but I'm not able to share that one. 1 second.
So present now option.
Yeah, present and then your entire screen, a window or a tab.
Right. In present now option, then your entire screen. Share your entire
Entire screen. Okay.
screen. Put on the black screen. One screen will appear
Yeah.
and share, and press on the share tab. It will be highlighted.
No, it's not. It's not allowing me to say.
No, sir. Present now option and entire screen after
Okay.
appearing screen, there will be black screen in the inside. Right. It is coming. Sorry, it is coming.
It's coming now.
It's coming. It is coming. Now share your PPT, entire PPT, in the full screen. Right. Please make it full screen and hide the button. Right. Yes, I'll hide the button. Meet Google. Right. Okay. Absolutely right.
Okay.
Okay. Thank you, sir.
All right. Thank you very much for giving me a fantastic introduction. I don't deserve so much things.
No, sir,
I was just thinking so long ago everything I've received. Anyway, thank you all, and let me thank the organizers, particularly this madam and Sajal Das, Anirbanda, and many people I know of very well. I've been there many times. So today, let me tell you something about very fundamental and very simple and introductory stuff that all of you know of. And let me tell you, you can always stop me and ask me questions. Okay, don't think that questions which are asked, there is any stupid questions. Questions which are not asked are the stupid questions. Okay, so you should always clarify everything. So today my talk title is Introduction to Fundamentals and Applications of Valence Bond Theory, Molecular Orbital Theory, and Quantum Theory. And here are my coordinates. All right. So basically the topics that I'll be covering today has these many stuff, atom and atomic orbitals that all of you know of, light wave and light particles, molecular orbital theory, applications of molecular orbital theory, valence bond theory and hybridization, conjugated carbon, hybridization, and the stability. Then I will take one example, polyacetylene, and I will show you some of its excitations, some interesting excitations and their applications, and then go over to a little more complicated conjugated systems like nanoribbons of graphene and graphene itself, two-dimensional graphene. And I'll show you many of its applications and what has been done till 2015 or 2016 using graphene and many other things. All right. So with this, let me go over to first these 5 atomic orbitals and to valence bond theory. So basically, atoms, as all of you know, is of the order of 10 to the minus 10 meter, the angstrom order. In fact, in 600 BC, Conrad had suggested the elements are made up of tiny particles called atoms, cona. But then actually, to us scientists, it is the John Dalton in 1814 which came into being what is atom. That atoms of a given element are different from those of any other element. Atoms of one element can combine with atoms of the same or of other elements to form compounds. Atoms cannot be created, divided into smaller particles, or destroyed in chemical process. That's what was known in 1814. A chemical reaction simply changes the way atoms are grouped together. Okay, very simple definition of atoms and how atoms are joined together to form molecules, etc. So atoms are made up of 3 types of particles: electrons, which is a tiny particle; protons, which is 1840 times heavier than electron; and neutrons of similar mass as proton. These 3 particles have different properties. Electrons are tiny, very light particles and have negative electrical charges. In fact, they are fermions or obey Fermi-Dirac statistics. Protons are much larger and heavier than electrons and have the opposite charges, positive charge. And neutrons are large and heavy like protons. However, they have no charge. All right. And spin is there in electron as well as in nucleus, which contains protons and neutrons. I'll come into that maybe if somebody asks questions. So in a hydrogen atom, the nucleus is in the center, and atom moves around in a symmetrical manner. The ground state 1s, which is a spherically symmetric function, and these electrons can have either a particle nature or can have this wave nature. Okay, and that's what de Broglie, which had said that wave particle duality. So it can stay either in a particle form or in wave form. All right. And these are the spd orbitals, which all of you know. S orbital, which is spherically symmetrical, and p orbital, which is px, py, pz, three of them in Cartesian coordinates, and d orbital and f orbital, which is not seen in the book because they all of them are three-dimensional. Here are the f orbitals. Okay, x, y, z, z x square minus y square, and z cube. These are the f orbitals. So light waves till 1900, classical wave theory considered light uh, as a wave, and it described most of the phenomena. Then light is characterized by three things. One is amplitude, what is the height of the wave, and this is the amplitude. This is the amplitude from this 0 to this height. Okay, this much. This is the amplitude. Then frequency and wavelength. This is wavelength between two maxima or two minima wavelength, and inverse of that one is the frequency. Okay, and energy, actually energy of this wave is a proportional to the amplitude square. It's modulus amplitude square, and or energy of the wave is proportional to 1 by this lambda, the wavelength. So the wavelength is lower, energy is higher. All right. With these two things in mind, let us look at some of the effects. In the early 20th century, several effects were observed which could not be understood using the wave theory of light. For example, there are two of them, the photoelectric effect and the Compton effect. These two are there, and I will discuss only one of them, that the photoelectric effect, which was described by Einstein. So Einstein tried this thought experiment classically. Method 1, increase the energy by increasing the amplitude. Remember, energy is energy increases with amplitude square. Okay, and if you reduce the wavelength, energy increases. So if you increase the energy by increasing the amplitude, what happens? So you have a screen in which whether you are seeing whether the electrons are emitted or not, and you increase the amplitude. No, it's not emitting. Increase further. No, it does not emit. Increase much further. It does not emit. In fact, if you increase large amplitude also, it does not. In a metal, from metal, electrons are not coming out, not emitting. There are free electrons on the surface of a metal. However, if you try to do the other way, reducing the wavelength with fixed amplitude, but reduce the wavelength so that energy increases. Same thing you do with a large wavelength. Electrons emitted, no. Reduce the wavelength by a little bit, yes, with low kinetic energy. Reduce further, yes, with high kinetic energy. So basically, this proves that no electrons are emitted until the frequency of the light exceeded a critical frequency, at which point electrons are emitted from the surface. Remember, smaller lambda means larger nu or larger energy. So basically, this is the photoelectric effect, and Einstein described it this way. The electrons are attracted to the positively charged nucleus by the electric force, which is an atom. In metals, the outermost electrons are not rigidly bound and can easily be liberated from the shackles of its atom. It just takes sufficient energy. Classically, if we increase the energy of an electromagnetic wave by increasing the intensity, the amplitude increase means increasing the intensity or brightness of a wave. Okay, energy increases, but the whole energy increases, total energy increases. Okay, brightness increases. However, if you think that light is made up of particles, then the light particles must have sufficient energy to free the electron from the atomic force. Increasing the amplitude is simply increasing the number of light particles, but it is not increasing the energy of each particle. Okay, increasing the amplitude does not help. However, if the energy of these light particles is related to their frequency, this would explain why higher frequency light can knock the electrons out of their atoms, but low frequency light cannot. So basically, when you increase the amplitude, the number of these particles are increasing. Okay, but each particle's energy is not increasing. But if you change the lambda, if you reduce the lambda, energy of the each particle is increasing, and the total energy also increasing this way. All right, these are the two views. Because they're made up of particles, if you think this wave is made up of particles, then only you can explain this photoelectric effect. In this quantum mechanical picture, the energy of the light particles of photon must overcome the binding energy of the electron to the nucleus. Each particle is knocking out one electron. Okay, if the energy of the photon exceeds the binding energy, the electron is emitted. Okay, the energy of the photon is given by h nu, where the constant h is this Planck's constant. All right, and the light particles before collision and after collision. All right, so let me tell a little bit about photons. Quantum theory describes light made up of particles called photons. They are bosonic particles. Remember, the bosons are named after or S.N. Bose. Okay, Satyendrath Bose. According to quantum theory, a photon has an energy given by E equals h nu equals hc by lambda. After the scientist Max Planck, the energy of the light is proportional to the frequency, inversely proportional to the wavelength. The higher the frequency, lower wavelength, the higher is the energy of the photon. In fact, the quantum theory describes experiments to astonishing precision, whereas the classical wave description cannot, given for these atomic systems, atom or molecules. So as all of you know, electromagnetic spectrum, it has the spectrum from 10 to the minus 6 nanometer to 100 kilometer. And radio waves, microwaves, visible spectrum only is here. This much, 400 to 700 nanometer, from violet to red, Vibgyor. In fact, shorter wavelength means most energetic photons. Longest wavelength means least energetic photons. So gamma rays is a much shorter wavelength, and radio is much longer wavelength. All right, microwaves is here, X-rays are here. All right. So what is quantum theory? Quantum theory is a theory needed to describe matters on a microscopic scale, such as on the scale of atoms, molecules, electrons, protons, etc. Classical theories are due to the Newton, that mechanical motion of objects, the force equals mass into acceleration. The Maxwell defined light as a wave. Neither of these theories quite work for atoms, molecules, etc. Okay. In fact, if I look at quantum in the dictionary, Oxford Dictionary, Merriam-Webster Dictionary, it says any of the very small increments or parcels into which many forms of energy are subdivided. That's what is quantum. All right. So since we are dealing with chemical systems, bonding is very important. Chemical compounds are formed by the joining of two or more atoms. A stable compound occurs when the total energy of the combination has lower energy than the separated atoms. The bound state implies a net attractive force between the atoms. It's a chemical bond. In fact, there are various types of bonds. Ionic bond, in which one or more electrons from one atom are removed and attached to another atom, resulting in positive and negative ions which attract each other, A plus and B minus. Covalent bond in which one or more pairs of electrons are shared by two atoms. Hydrogen bonding, very weak interactions with a highly electronegative element like oxygen, nitrogen, and sulfur, another electronegative atom through the hydrogen bonding. In fact, this X1 to H is a covalent bond, and H to X2, that's the hydrogen bond. Okay, so I'm showing you pictorially this chemical bonding. Ionic bonding, for example, sodium chloride, sodium plus and chloride minus. Covalent bonding, you have this ClBr or any other covalent system. And metallic bonding, these are all the free electrons are there on the surface, metallic. And hydrogen bonding, this is an example of hydrogen bonding. There are many, urea to many biological systems, everything is controlled by the hydrogen bonding. All right, so In fact, there have been so many informations from this chemical theory, this molecular orbital and valence bond theory, that periodic table, for example, I've put here a periodic table where the this hydrogen, lithium, beryllium, sodium, magnesium, potassium, calcium, rubidium. These are on the left side, and ions like oxygen, fluorine, sulfur, chloride. These are all on the right side. Okay. Elements from opposite ends of the periodic table in general form ionic bonds. Large differences in electronegativity, and the elements with large electronegativity are in the upper right of the periodic table, while the elements with smaller electronegativity are on the bottom left. If these extremes are combined, such as in rubidium fluoride, the diffusion energy is large. The hydrogen is the exception to that rule, forming covalent bonds. Elements which are close together in the electronegative um, in electronegativity tend to form covalent bonds. Okay, these are some of the hand waving rules which are there. Most often, these are they follow these rules. So the father figure in chemical bonding is G and Lewis, from 1875 to 1946. Electron distribution can be depicted with Lewis electron dot structures in molecules. The electrons are distributed as shared or bond pairs. For example, the shared or bond pair. Lone pairs are there in chlorine. So Lewis structure, there are some rules, and for example, number of bond pairs plus number of lone pairs, it's called octet rule. This is due to the fact that all the atoms always try to obtain the electronic configuration of nearest inert gas, which is a very stable electronic configuration. There is no more inert anyway, because many of the compounds have been formed by Xc and other inert gases. The number of valence electrons in an inert gas atom is 2n square, where n is the period number. So all the atoms always try to make their valence electrons number 2n square. For second period, the octet rule comes as 8. 2n square. So 2 to the square, 4 into 2, 8. All right. So molecular orbital theory is a delocalized electronic theory, quantum mechanical treatment of molecules similar to that used for isolated atoms. It invokes the concept of molecular orbitals, and is a very famous combination, linear combination of atomic orbitals which are involved in molecular orbital theory. It exploits the wave-like properties of matter, the electrons which are not considered as particle but like a wave. So central themes of molecular orbital theory. Okay, the molecule is viewed on a quantum mechanical level as a collection of nuclei surrounded by delocalized molecular orbitals. Okay. Atomic wave functions combine to give rise to molecular wave functions. If wave functions reinforce each other, a bonding molecular orbital is formed, a region of high electron density between the nuclei. And if wave functions cancel each other, an anti-bonding molecular orbital is formed, a node of zero electron density between the nuclei. All of you, please listen to this one, that the wave functions reinforce each other. A bonding MO is formed, region of high electron density between the nuclei. That means the electron they share electrons. That means both are electronegative ions, electron, and they come closer. Remember, the interaction is 1 by r, e square by r. So r becomes 0, e square by r becomes infinite interactions. How it gives stability, I will ask you, we'll discuss at the end. All right. Now, an analogy between light waves and atomic wave functions I will give. For example, here the amplitude of wave functions added, that's in bonding molecular orbital, and are subtracted, it cancel each other in an anti-bonding molecular orbital. So bonding and anti-bonding molecular orbitals which are drawn here. This is bonding molecular orbital where they share the electrons in intermetallic interbonding region within the bond, in the middle of the bond. And anti-bonding molecular orbital, in fact, there is a node in the bonding region. That means zero probability. Okay, number of atomic orbitals combined actually will give you number of molecular orbitals produced. Okay, bonding molecular orbital lower in energy than isolated atoms. Anti-bonding molecular orbital higher in energy than isolated atoms. To form a molecular orbitals, atomic orbital must have similar energy and orientations. The symmetry is very important. Sigma and pi bonds are denoted as before, and the star is used to denote antibonding molecular orbital. And sigma bondings are positive combinations, and pi bonding is negative combinations, antibonding combinations. For example, why does benzene resist addition and prefer substitution? If benzene were to undergo addition, resonance would be disrupted, and this would render the structure less stable. Therefore, benzene prefers to substitute and maintain resonance. What is benzene possesses 6 bonds intermediate between C double bond C and CC. According to resonance, the bonds are not single bond or double bond, but a hybrid of the two. In fact, the X-ray studies were done and shown that all bond lengths are same. So resonance can be considered as the condition occurring when more than one valid Lewis pairs can be written for a particular molecule. This can happen anytime if there are two or more adjacent p-type orbitals in the same plane. Resonance structures are hypothetical. They represent extremes of electron location. Resonance can be considered as a valence bond solution to a molecular orbital problem. A resonance structure must have the same number of electrons. Rule 1. Rule 2. All resonance structure must be valid Lewis dot structures. The hybridization does not change between resonance structures. The positions of atoms are the same in all structures. Resonance structures do not have to be equivalent. So the most important contributor, maximum number of atoms with full octet, and formal charge, the most important contributor, also has these charges, and they are willing to accommodate them. The most significant contributor has the maximum number of covalent bonds. The most significant contributor will have the least number of formal charge. The most significant contributor has the least number of unpaired electrons. These are some of the preferences for me. Let me introduce to you something which is hyperconjugation. In fact, I will tell a little bit about it, a theory behind this. Hyperconjugation in organic chemistry is a stabilizing interaction. The results from the interactions of the electrons in a sigma bond, usually CH or CC, carbon-carbon or carbon-hydrogen, with an adjacent empty or partially filled antibonding pi orbital, to give an extended molecular orbital that increases the stability of the system. Only electrons in bonds that are beta to the positively charged carbon can stabilize a carbocation by hyperconjugation. Hyperconjugation can be used for rationalizing a variety of chemical phenomena, including the anomeric effect, the Gauss effect, the rotational barrier of ethane, the beta silicon effect, and the vibration frequency of exocyclic carbonyl groups. Hyperconjugation has also been shown to be the correct explanation for the preference for the staggered conformations. I will come to that. 2001, there was a Nature paper. I will come to that one later. So hyperconjugation is a factor in explaining why increasing the number of alkyl substituents on a carbocation or radical center leads to an increase in stability. Okay, because of that, because of hyperconjugation. So the point is, the stabilization arises because the orbital interaction leads to the electrons being in a lower energy orbital. That's the stability. So the ethyl cation has a 3 CH sigma bonds that can be involved in hyperconjugation. The more hyperconjugation there is, the greater the stabilization of the system. So for example, the tertiary butyl cation has 9 CH sigma bonds that can be involved in hyperconjugation. Hence, CH3C plus is more stable than the other guys. So I'll come to this one, ethane rotational barrier. Everybody knows from eclipse to trans configuration, this energy difference is 3 kcal per mole. So staggered and eclipsed, carbon-carbon bond length is 1.54. And all these books is written, Eliel, March, Morrison, Boyd, Fina, that it's because of steric effects, staggered is stabler than eclipse conformation. Okay. For CH3, the bond length is 1.54 angstrom, and staggered is favorable by 3 kcal per mole, kilocal per mole. And even for SiH3, silicon in place of carbon, the bond length is 2.35 angstrom. Staggered is favorable by 1 kcal per mole. The steric effect decreasing, but rotational barrier becomes constant. Okay, because the bond length is larger for silicon, SiH3. The point is, there is a paper in Nature 2001, 2001 Nature paper, which said that it is a hyperconjugation, not steric effect, which makes the staggered stabler than the eclipse conformation. In fact, hyperconjugation was introduced by R. Mulliken to explain the bathochromic effect in toluene by 18 nanometer. When you go from benzene to toluene, the change 18 nanometer. Okay. However, this bond, toluene, this is sigma bond. The sigma bond, how can it interact with the pi electrons of the benzene ring? But because of the hyperconjugation. All right. So exactly what is the what is it actually? I will show you a little bit mathematically. Very simple way. So basically, think about this one. There's a benzene and you have CH3 group. There's a single bond and CH3. So think of this one as pH, that is benzene plus carbon plus H3. There are 3 hydrogen. Symmetrically, I'm placing like a triangle. Okay. It's a good assumption as the 3H and CH3 have a D3H symmetry. So one can have a 3H like this. So one can write down 3 atomic orbitals, 1s atomic orbital of hydrogen. So 3 molecular orbitals will form. These are the 3 molecular orbitals. One is ABC, 1s, 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 or A hydrogen, B hydrogen, and C hydrogen, all positive, and A minus half of B minus half of C. Okay, and the third one is B minus C. This is pi type orbital. Okay, there is a minus is there. Both are minus, antisymmetric combinations. And this one also is pi orbital because there is a minus sign. So you form 3 molecular orbitals, which is 1 sigma and 2 pi type orbitals. Okay. So what you have is there is a pH, a single bond to carbon, and there are 3 bonds to H3 as an object. And out of the 3 bonds, 2 of them are pi type and 1 is sigma. So in fact, one of the pi type, it can involve with the benzene to carbon and to the benzene. Okay, that's the hyperconjugation. And this is what explained by Mulliken in 1950. And about this Nature paper, the paper still exists, but there have been almost 10 papers. We also contributed to some extent, which proved that this is wrong. The steric effect is the correct explanation, which is there in the textbook. Okay, not hyperconjugation. Okay, and so for example, but our calculations show that hyperconjugation is a weak force and it is the steric interaction that stabilizes the staggered form. So the textbook are actually correct. All right. So let me move on. I would like to ask if there is any questions you can ask me here. No question? Okay. Okay, let me proceed. Now we'll talk about this conjugated carbon. Hello? Yeah? Okay. Conjugated carbon, hybridization stability, polyacetylene, excitation application, graphene, and nanoribbon various applications. So this is a periodic table and carbon. This element has been used heavily and organic chemists use that one. This one almost, it's like a default one. So carbon, which has 6 electrons and it's 12.001. Okay. So its applications are huge. Plastic, sticks of wine, and compressed charcoal, pencil lead, graphite, alloy with iron, steel, silicon carbide, cloth of oven carbon filaments, etc., etc. Heavily used actually. Many household stuff also is made up of carbon. Allotropes of carbon, diamond, such a beautiful thing, so costly, so expensive. Graphite, which is used in pencil. And then there are many others, amorphous carbon, carbon nanotube, fullerenes, and other things have been used. Okay. In fact, it is one of the elements in the periodic table which can have all the hybridization which is possible hybridization. For example, you can have the sp hybridization, sp2, and sp3 hybridization. a linear combination of atomic orbitals. sp3, the first one is sp3, the 3p and 1s, mostly p type orbital, and there is a sp2, 2p type and 1s type, and sp, 1s type and 1p type combination. This is the structure. 180 tetrahedral, it forms a planar one, and this one is a linear one, sp hybrid orbitals. So this is the unit of tetrahedral unit, sp3 carbon, sp2 carbon trigonal planar, and linear one is sp orbitals. Okay, carbon can form single, double, and triple bonds. These are the smallest building blocks of all carbon materials. Okay, these are the guys. sp3 carbon, sp2 carbon, sp carbon. All right, let me start with this carbon compounds, cyclopropene, which is difficult to isolate, three of them, strained structure, okay, because three of them, a triangular structure. Cyclobutadiene, extremely unstable, okay, it's anti-aromatic. Cyclopentadiene, five of them. I will come to this cyclobutadiene a little later, okay, in more detail. Benzene, which is used heavily, is a colorless liquid, isolation by Faraday in 1825, and Kekulé had given the structure of benzene 1865. Cycloheptatriene, a non-planar molecule widely used in organometallics. Cyclooctatetraene, an inflammable non-aromatic colorless liquid, exists in both, more stable, and twisted chair form, are less stable. Okay. So these are can be nicely done in terms of linear combination of atomic orbitals. Only the pi orbitals one could take and can form the molecular orbital. Okay. For example, here are some molecular orbitals I've drawn for four guys. So one and two degenerate guys, and then one more molecular orbital which is anti-bonding molecular orbital. These are like non-bonding orbitals. So you have one electron, two electron, four electrons are placed like this, or five-membered ring. You have two, two, and two here. So 6 electrons can be put like this. For benzene, it's like benzene structure. So you have ground state, which is pi type, pi 1, the pi 2, pi 3 are degenerate, pi 4, pi 5 are degenerate, empty, and pi 6 is non-degenerate at the highest energy. So 6 electron can be placed here, and this is aromatic. So let me tell you this um, you know, this is a four-membered ring. Or this is done as six-membered ring. For example, the chain of hexatriene. So you have this six orbitals. There are no more degeneracy. So three here in the bonding and three anti-bonding molecular orbitals for hexatriene. Not cyclic. Benzene has this structure, you know, two, both the middle two sets are doubly degenerate because there's a ring structure that gives a degeneracy. But if you open it up, hexatriene, you have this no degeneracy. Each one is non-degenerate orbitals, molecular orbitals, symmetric, antisymmetric, symmetric, antisymmetric, symmetric, antisymmetric. Okay, as you can see, there is no node in the ground state. Okay, they all are positive this side, and down all are negative. However, when you go to the next one, there is one node, all positive here, all negative here, then negative, then positive. So one it goes through zero, one only through the middle. Okay, this is asymmetric. Then it is symmetric. This is again in such a way it is drawn. There are two places, two sides, two carbon through bonds through which the probability is zero. So this is zero node, one node, two node. This is three nodes, 1, 2, 3 nodes. Then there are four nodes, 1, 2, 3, 4. Then there are five nodes, 1, 2, 3, 4, 5. All of them antisymmetric. So from zero node to five nodes, one can draw this molecular orbital of hexatriene. It's a chain system, not ring. Okay. And in case of ring, This is benzene. You have this bonding molecular orbital. And then you have this, there is a node here, but both can be there. And there are two nodes here. Again, both can be there because they are degenerate, and you have three nodes here. All right. Now let me tell you about this. Everybody knows Huckel's pi electron rule. 4n plus 2 is aromatic. Otherwise, it is not. For example, benzene, which is aromatic, there are 6 electrons, 4n plus 2. So n is 1. Or 5-membered ring with a minus sign, this gives an extra electron. So you have this 6 electrons. So this is also aromatic. However, if you have a this is a octet, this is a 8-membered rings, the cation, cyclopentadienyl cation. For example, here it is 7 and 5. It becomes plus and minus, both becomes aromatic. Plus, this is also 6 electrons and can be aromatic. However, this cyclobutadiene, it has these 4 electrons. 2 are in the middle, singly occupied orbital, and they are anti-aromatic. All right. Cyclopentadienyl anion and tropylium cations are aromatic, but neutral cyclopentadiene or cyclopentaheptatriene are not aromatic. As a consequence, azulene stabilizes in dipolar structure. The 7 and 5, it becomes like 7 plus, for example, here, this one, and this 5-membered ring minus, which is here. All right. Little more on cyclobutadiene. So the bond length alternation, if you make it square, so bond length is 0, and all the bonds are same, you make, in fact, this is not a stable structure. So you put a Ion-Taylor distortion, electron vibrations coupling, if you introduce, then it becomes either this one, the 2 bonds are shorter, these 2 bonds, or these up and lower one also can be shorter. So the bond length alternation is 0.245. The bond length between this double bond and single bond minus double bond is this much. Okay. So you have this structure. But if you can make these 2 guys coming down, the 4 electron, this is what happens. So 4 electrons, it becomes unstable. All right. So in C4H4 is anti-aromatic and unstable. How to stabilize it? In fact, when it was discovered, after that it took 30 years. This professor, H.C. Langford Higgins, who was a professor in Britain, just passed away recently, 2004, published a landmark paper. Remember, that time computers were not there. He was doing by hand, actually. Okay. In 1956, Journal of Chemical Society, he published this paper in 1956 that he used to do by hand molecular orbital theory. It was hand notes which he published in Journal of Chemical Society. He basically suggested that, well, you unstable molecule, you make it complex, then it will be stable. He suggested that C4H4 plus a metal, which is low energy, electrons are there in the metal, which will go to 2 plus, metal 2 plus, and 2 minus, it will give it to the C4H4. C4H4 2 minus will have 6 pi electrons, it will be aromatic, and metal will be 2 plus. So metal will be tensile metals having low energy d pi orbital for interaction with the pi molecular orbital of C4H4. So he suggested this compound, and actual synthesis was 2 years after his suggestion. So Journal of Chemical Society 1956 and 1958, the same journal, the synthesis was published. All right. And what he suggested? This system. The eta 4 complex C4H4 FeCO3, sandwich complex FeCO3, and you can have this. It's a second order Ion-Taylor distortion. It goes through a symmetric structure, intermediate, which is high energy, and it forms these 2 dimeric structures. Either the short bonds is along these 2 or the other 2. Okay, C2H and C2H structure, complexation, it forms, it stabilizes. Right. So eta 4, C4H4, FeCO3. In fact, even today, this is the only molecule with cyclobutadiene available even today. One can buy it. There is no other molecule which stabilizes the C4H4. It was synthesized in 1958, which was published in Journal of Chemical Society. Soon after this Langmuir-Higgins paper in 1956. Okay, this is the power of molecular orbital theory. Okay, let me go over and slowly tell you about little more on this naphthalene, anthracene, or polyacene, or phenanthrene, pyrene, coronine, or you can go up to the two-dimensional graphene. Okay, in fact, the simplest polymer is the polyacetylene. Organic polymers are synthesized through reactions of functional groups of monomers. In general, same catalysts are used to stimulate the opening up of the unsaturated bonds. A prototype example is NCH, triple bond CH, it gives rise to this polyacetylene, CH, double bond CHN. Polyacetylene is the simplest polymer and a member of the large class of vinyl polymers like this. For example, cumulin, C double bond C, C double bond C, double bond C. Every carbon is having four bonds. Okay, cumulin. But as soon as you try to synthesize this one, it will convert to this guy, polycarbine, triple bond, single bond, triple bond, single bond. So this is never stable. Cumulin is never stable at this form, in this form, all double bond. Okay, it goes to this structure. In fact, try to think about it. As I will keep on telling, the answers are there. But if you do not still know, I will ask you this question at the end of my talk. So polyacetylene is a planar bond dimensional system. Roughly, the carbon bond angle is 120 degree, while the average bond length is 1.4 angstrom. For a long time, polymers were considered good insulators. In fact, they are very good insulators. Remember the black electrical switches made of bakelite that even now all people use. In 1977, this concept changed radically. Polyacetylene became the first organic low-dimensional metal. With doping, the conductivity of polymers can be increased to 10 to the power 7 Siemens per centimeter. Remember, copper, which is a conductor, is 10 to the power 6 Siemens per centimeter. So the polymer is having much more conductivity than even copper and silver. The conductivity. Okay, so and the polyacetylene can be in four structural forms: isomers, trans-transoid, cis-transoid, trans-cisoid, and cis-cisoid. This is a helical structure. But generally, you find it in trans-transoid structure. Okay. In fact, this paper which created the history, electrical conductivity in doped polyacetylene. Okay, these three people got Nobel Prize: Higa, McDermott, and Shirakawa. So Shirakawa, McDermott, and Higa, these three people got Nobel Prize. This paper, which was published in 1977 in PRL, Physical Review Letters. Polyacetylene, a dull black material, became shiny metallic on exposure to dopant vapors, and it created something called synthetic metal. In fact, there is a journal, Elsevier journal, called Synthetic Metals. That also was original. This came out that there is a journal named Synthetic Metal. Soon after this paper was published. So what was there in this paper? Let me tell you in detail. Basic observation in this paper. They were measuring optical absorption of pristine polyacetylene. It's like a semiconductor with a gap of 1.4 electron volt. Upon doping, an additional peak appears in the gap region. However, that peak does not depend on dopant. Also, at other position, those peaks do not depend on the dopant. Pure polyacetylene exhibits Curie paramagnetism. That means temperature independent paramagnetism. Sorry, inverse of temperature paramagnetism. They have done ESR, NMR, Endor, and they find that the spins are spread over 15 to 20 CH units. One spin half in 15 to 20 CH units. Upon doping, okay, remember this paper, this doping was done with great conductivity or trans polyacetylene as a function of ASP6 dopant Okay, and SBP6 actually. And so pure polyester exhibits Curie paramagnetism, that is 1 by temperature. Okay, the susceptibility goes at 1 by temperature. Upon doping, the Curie paramagnetism drops while the conductivity goes up. Remember, it was not conductor, it was paramagnetic, that is magnetism it is showing up, whereas this one, paramagnetism reduces, but conductivity goes up. That means electrical conductivity goes up. Near 1% of doping, the electrical conductivity shows a drastic change in the magnitude and temperature dependence. It resembles metal and fluid transition. However, Pauli paramagnetism, which does not depend on temperature, this is a temperature independent paramagnetism, does not show up at 1%. Rather, at 6% doping, magnetic moment increases. Polystyrene, though a simplest organic polymer, it is more complicated than conventional inorganic semiconductors like silicon, germanium, etc. Difficult even to determine the molecular weight, actual structure, or dopant content are sensitive to synthetic conditions. Various defects like cross-links, head-to-head, or head-to-tail are inevitable. So basically, what these people found is that if they increase the magnetism, the conductivity reduces, electrical conductivity reduces. And when the electrical conductivity increases, magnetism decreases. It's like a reverse spin charge. If the spin is there, charge does not show. If the charge is there, spin does not show. Okay, that's what they found. Okay. So, in fact, they did a theoretical estimate of this one, that there is a chain only, interchain coupling is very, very small. So, this is a chain system, and there is a dimerization which opens up a gap, but it stabilizes the system, makes it an insulator. It stabilizes, makes it an insulator, and opens up a gap, but it stabilizes the system. Because of this bond length alternation, the even sides shift to the left and odd sides shift to the right in phase. Without this bond length alternation, the polyester is symmetric about deflection in any plane perpendicular to the chain and through a CH group. Deflection brings the phase A to phase B. There's a single bond, double bond, single bond, double bond. Then you have double bond, single bond, double bond, single bond. Okay. There's a symmetry breaking happens. Both of them have the same energy. By the way. In fact, there is a phase transition. Okay, this is a little bit of symmetry breaking, etc. I think it's a little bit of physics stuff. So I'll not come to that one. In fact, since there are two degenerate ground states, there is a kink, or the defect states appears. It's a misfit. For example, think about this one. Think about a ferromagnet. So you have all up spin throughout a one-dimensional chain, let's say, on all up spin. Now, how will you make an excitations? If you make one up spin to be down, then you are affecting two exchanges, right? Neighboring two exchanges will change. However, if you do it like this, like which is drawn here, okay, two things are red now. Okay, two things. If you make this one to be up to down, then you are affecting, this is antiferromagnetic, this is also antiferromagnetic. Okay. However, if you make all these are up, then this side, all of them are down. They are ferromagnetic. Then you are affecting only one guy. Okay. And this also, you can change it in such a way that over a length of spin, this change happens from up to down. Okay. So there is a domain which gets created. Okay. Which happens in a ferromagnet. For example, as you know, iron is a ferromagnet. And you know what is a TC? TC is 1040 Kelvin is a TC of iron. That means below 1040 Kelvin, it should be a ferromagnet. But you try to bring in a pin, does it attract? It does not attract. But take this ferromagnet, a ball, iron ball, and hit it on the ground. Okay, hit on the ground, same place. Hit quite a few times. You hit, you will find near the where you are hitting, bring a small pin, you will see it will attract for some time. Then again it goes off. Okay, that's because it breaks up into domains, various types of domains. Okay, because there is an interaction called dipolar interaction. To reduce the dipolar interactions, these magnets, they break up into various domains and it remains in the domain structure. And when you're hitting, one domain becomes smaller and the other domain grows. at the expense of the other domain. So you have net moment comes up actually, and that's why it attracts. Okay, this is a very different kind of thing. The domain motion, etc., very similar to the NMR T1 and T2. So, for example, here I have drawn double bond, single bond, double bond, single bond. Then here there's a kink or misfit because this side I have single bond, double bond, single bond, double bond. Okay, the two ground state I have put on both sides, and in between there is a kink or there is a misfit. All right, and that is what the soliton is. Soliton was discovered by a British a Britisher. Simple. He was not a scientist or anything. One day he was standing near the small stream. Stream is a river, which is a small river, small width river. Okay, and he found that there is a boat which was coming with too many people in it, and it went very fast. Okay, and then he found that the wave that it created, by displacing the water, that wave remained for a long distance actually, and he told there it's a solitonic wave because you have a misfit. For example, I've drawn here, this misfit can be anywhere in the chain. On the left, it is one ground state, right, other ground state. So because of that, these are called solitons. Solitons are very interesting quasi-particle. So for example, coupling between single and double bonds generate bonds instead of states. So you have antibonding and bonding molecular orbital, switching the bonds pattern. So for example, double bond gives bonding, single bond is anti-bonding, and defect state is a non-bonding one. Now if you have a chain structure, there is a defect state which is non-bonding, okay, and it has an unpaired electron, but the whole system is neutral. So you have a spin, which is spin half in the non-bonding orbital, which spin half is there, but the whole system is neutral. You try to put an electron there, then it will go with the down spin, the up spin and down spin, it is zero spin, but there is a charge now because you have put an electron. Or take out an electron, the up spin goes. That means you have zero spin there in the non-bonding orbital, but it has a charge, positive charge. So remove this, S equals 0, charge become minus plus E, add another electron, S equals 0, charge become minus E. So a reverse spin charge relationship. That means if you have spin there, charge is 0. If there is charge is there, spin is not there. Okay. So the solitons are reverse spin charge relationship. But if there is a soliton, you'll have an anti-soliton also. So you have, in fact, this it does not happen like that. That one site over a particular site and it's a domain length, etc. Even number of carbon, there is a soliton and anti-soliton pairs come in. Okay. In fact, when an electron moves in an ionic solid, its surrounding media gets polarized. Relative motion of opposite ions, polarization fields. The complex moving electron and its polarization field is called a polaron. That means the electron is not alone; it is get dressed up with the vibrations. Okay, that's called polaron. Polarons are extremely important in ionic crystals and polar semiconductors. Bipolarons are not two polarons; they are also polarons, but of different type. They are elementary excitations in a non-degenerate ionic crystal, first observed by Su and Schrieffer. But in general, in a conjugated system and in many of the inorganic systems, oxides and other things, it is not an soliton, the exciton, which is the basic excitation. Exciton actually is a bound electron hole pair. And there are various types of excitons, like one-year exciton, Frankel excitons, charge transfer excitons, and many other excitons, bond pair excitons, etc. And you can have bi-exciton, tri-exciton, exciton strings, and large number of excitons. Okay. After their generation, the excitonic generation, recombination, if they recombine, electron hole recombine, you get light used in the light emitting diode applications, OLED or LED for inorganic systems. Or if you collect this electron and hole in anode and cathode respectively, you get current used in photovoltaics. So these excitons, if they recombine, you get light. If you can take this electron hole to the to different electrode, you get current in the outer circuit. That is photovoltaics. You create this exciton through the light, and you can collect the electron and hole at the in the outer circuit to get current. In fact, this how it goes, the electron and hole, that is called mobility, because there is some electric field which is there, and its velocity modified due to the electric field, and it's called mobility, charge carrier mobility. It's a fundamental property. It is very important. We need to know mobility for designing field effect transistor and photovoltaics. Requirement is the very high electron hole mobility at room temperature. So the electron hole should fast reach the electrodes so that you get current very fast. In fact, there are primary types of carrier actions occur inside a material. Drift, the charged particle motion under the influence of an electric field. Okay, limits the current flow in a MOSFET device, metal organic semiconductor, field effect transistor, or photovoltaics. Diffusion, particle motion due to concentration gradient or temperature gradient, limits the current flow in a PN junction, PN diode. Recombination separation, computing process for designing a LED, light emitting diode, and a solar cell or photovoltaics. So basically, what one does is for drift, drift is the main thing because there is electric field induced electronic motion, electron hole motion. In fact, carrier mobility, electron hole mobility, there are two pictures in the literature. One is a localized picture. In a molecular solid, you have these electrons in a molecule would hop between localized states, that is molecular states, by the assistance of phonons or molecular vibrations. It's a small Polaron model, which is given by this Marcus theory, Rudolf Marcus, a Nobel laureate in Review of Modern Physics. And this is used applicable for most of the molecular solids. Then there is another one called delocalized picture. Electrons are dressed by the phonons, forms polarons. Electron phonon scattering plays crucial role, central role. This is given by the Boltzmann transport equations. It can describe the carrier mobility in covalently bonded inorganic semiconductors and polymers. This was given by, again, two Nobel laureates, John Bardeen and Shockley. It was a physical review paper in 1950. In fact, here we have developed in-house codes within both the above pictures. We keep doing for molecular solid and even for inorganic crystals, various oxides to very large number of systems. We work on these things. So these Boltzmann transport equations, we have written our in-house codes to do these calculations. Okay, so to go over, let me tell you that these organic molecular systems form this pi stacking in graphite, this benzene dimer. For example, you can have parallel stacking, but shifted, slip parallel, or T-shaped stacking, CH pi interactions. Okay. In benzene, there are two types of crystals which are there, benzene crystals. One is P21 by C, a benzene crystal. During the 1949-50, these two crystals were crystallized forms were obtained. Two nature papers are there. Benzene, another benzene, PbCa. This is the crystal structure. These two crystal structure. Dimer arrangements in benzene 1 is this type, and in benzene 2, this PbCa, you have this type. Let me just tell you that there is a nice rule which everybody knows. It is used to determine stability. Clark's rule. Okay, it indicates that the most stable structure of an annulated benzene is the one possessing the maximal number of aromatic sextates separated by the entirely empty six-membered rings. The pi electrons tend to be semi-localized in disjoint pi sextates, which form isolated aromatic islands surrounded by pi electron or empty rings, the gaps. So yeah, among these structures, tell me which one will be more stable? A, B, or C? This is the pi sextate, by the way. According to class 2, the most stable structure is A, not B or C. Okay, because each one sextate is surrounded by the empty ones, rings, empty six-membered rings. Okay, now I'll write down quite a few structures. Tell me the first one. Is it a stable structure? I cannot hear anything. Yes or no? No. Second one? No. Third one? Yes.
Yes.
Fourth one? Yes.
Yes, sir.
No, 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 actually, because these other guys are
There is a
there.
double one, sir. Yes.
Okay, fifth one? Yes. Sixth one?
No.
No, sir.
No, yes. Because look
Sir,
at the surrounding of this one. Surrounding of these two. Okay, middle guy.
Sir, but triple bond is there. C triple bond.
Triple bond is the other ring which is there other side.
Okay, sir. Okay, sir.
Yeah. Seventh one? Yes.
Yes, sir.
Eighth one? No.
No.
Yeah. Ninth one? No.
No.
10th one?
No, sir.
11th one?
Yes.
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 12th?
No.
No, sir.
No, yes. Because,
Yes.
well, let me tell you, this paper is there. The Wasman et al. Physical Review letter, 2008. This is the reference. To write down 101, the volume number, 96402 is the page number. And in fact, this paper exists where they have drawn many structures, and they have told which one is stable, which is not stable, due to class rule. Okay?
Sir, is there any similarity with Fry's rule?
Very similarity, exactly. Similarity is there.
Yes,
But
sir.
they
In
have
Fry's
used this
rules
class
also,
rule.
maximum number remain in benzenoid form.
Yes, the CLAR is CLAR, not CLUR. Sorry, there's a mistake I made actually. It's a CLAR. Okay, CLAR.
Okay, sir.
Yeah. So they have used the
But
class rule.
12,
And to look at
number
which structure
12, there is a two 5-membered rings we can see. So how it becomes more stable? The 12 number, there's 6-membered and empty 5-member.
Yeah, but this side is CH2. See, 5-member, you have a CH2 there.
Okay.
But ring is there other side, na?
Sir.
This side.
Okay.
Yeah. 5-member also you have two bonds and pi bonds will be there.
Exactly.
Beautiful. You can look at this paper. More detail will be there.
So there will be no angle strain.
No, it will not be planar, of course.
Okay.
We are not talking about the planarity, but how the stable structure or not, is energetically stable or not.
Okay.
In fact, after this one, they have done a calculation also, and shows that yes, class rule is properly valid here. Okay, these structures are stable, and many of the structures are not stable. But hand wavingly, by looking at only the structure, using the class rule, you can say whether it's stable or not. And those are also, while doing a high level calculation, also the same thing you get. Well, you get stability in terms of number, quantitative number. Here you do not get the quantitative number. Yes or no only you get. All right. So it's a beautiful example which is there in a journal, physical, very top journal in physics literature, and they use this class rule. Okay, and let me tell you that graphene, which got Nobel Prize in 2010, which is going to the guy named Novoselov. They did the mechanical exfoliation of single layer graphene, and there's this system, graphene two-dimensional system, two sublattice atoms, bipartite. The unit cell is a rhombus unit cell, which is drawn here, the shaded region. This is the unit cell. And because there are bipartite, so you have this k prime points in the band structure. Interestingly, the band structure near the Fermi level, this dispersion is linear. That is, Ek is plus minus Ch cross k. In general, you will find that free electron is k square. H cross is k square by 2m, but it is linear in k. Strictly non-interacting band picture because of the neighbors, the way neighboring atoms are there. Each carbon is having the 3 bonds, okay, and that produces such a band structure. Okay, it's a very interesting, extremely interesting system. In fact, graphene, which is a planar 2D two-dimensional system, well, there have been many theorems from 66, 68, many 37 also, in Landau to Marvin, Wagner, Parels. There are many theorems, many physics great guys. They have told that a two-dimensional pure 2D or pure 1D planar system would never exist, ceases to exist actually. Such a strong theorem. Even at zero temperature, quantum fluctuation will destroy the long range order. Okay, if I can talk about this one if you have any questions. So all these things are there. When they got this graphene and when they measured that what they got is in the X-ray crystal structure, this would have been a planar one, this would have been a sharp peaks. However, they got blurring of the peaks because it is like, this Indian sari. If you try to stretch it, there will be some parts which will have the surface normals will be there, blurred peaks because of some angle will be coming up. Okay, because of that. So it is not a purely planar two-dimensional system. You get blurred peaks in the X-ray because the incoherent superposition of surface normals. There are many surface normals you can draw through this surface, this kind of surface, OA star surface. All right. And now there are so many things, graphene nano ribbons. Oh, I sorry. Now can you hear me?
Yes, sir.
Sir.
No,
Yes,
no, there
sir.
was a power off and I had not joined. Okay. So anyway, so this is the armchair. As you can see, this is the armchair edge. If you cut down armchair edge, or you can have this zigzag edge.
Sir, we
Sir,
can't
you,
see your slides.
Or again, I have to do this. Can you hear now? Can you see now?
Yes.
Yes.
yes, sir.
Yes,
Okay,
sir.
okay. Sorry for this mess up. Okay. So there are two
Yes,
types
sir.
of edges you can form if you cut down the graphene to a ribbon structure. Okay, you can have a zigzag edge ribbon or you can have an armchair edge ribbon. These are all highly correlated systems. That means electron interactions are important here. So, for example, this is armchair edge. As you can see, this armchair, this edge structure, edge of this graphene nanoribbon is an armchair. Both sides you can see armchair edges, or you can have this zigzag edges. Okay, the zigzag edges. See the difference between the armchair and zigzag. All right, the edges. And there have been so many predictions that the zigzag edge structures will be metallic if you apply electric field. Then you can have a half metal. That means one type of spin will be metallic. It will the one type of spin will be conducting, but other spin will have an insulating. There's a half metal. Okay. Interestingly, this graphene, which is having a linear um, um, dispersion, pk is plus minus c h cross k. It's not a metal because there is no electron density at this k point. Okay. In fact, the electron density is 0. So it is called not a metal, it's semi-metal. It is called a half metal. For example, if one type of spin is conducting, other spin is insulating, it's called half metal. Okay. In fact, it can be used as a highly efficient memory storage device. Up and down spins can be used as on and off state respectively. Control over spins, so complete control over the memory storage one can have if you have these half metallic systems. So, for example, there have been many predictions and of this half metallic thing. So, for example, there are graphene nanoribbons productions in a German group, this Klaus Mullen's group. They do a bottom-up approach. They synthesize from small structure. They start with this, this 5 benzene rings with R group, and then keep on increasing and get a well-defined nanoribbon structure. Chemical route to smooth as graphene. For example, how graphene is cut upon oxidation. There was a theory paper. This was a theory paper which said that a carbonyl pair, if you try to put in between this in the bond in a CO group, presence of one epoxy bond or one epoxy pair activates the adjacent bonds for further epoxidation. The epoxide bonds form along a line. And these are the energy difference, and they said this is an electron volt. Okay. The interesting theoretical predictions of this paper in 2009, Jack's paper, 2009, motivated the experimentalists to synthesize smooth as graphene nanoribbon by longitudinal unzipping of carbon nanotubes. For example, longitudinal unzipping of carbon nanotube to form graphene nanoribbon. For example, same thing they did. KMNO4, H2SO4. So this is epoxy bond formation, and the double bond O, more double bond O, and then this gets cut actually. Okay, and you can see TM measure stepwise unzipping of carbon nanotube. And then there are many papers are there where graphene nanotube preparation with putting the bromine and uh, the heating that sample and various types of nanoribbon bottom up fabrication over this gold 111 or silver 111 surfaces. Graphene nanotube synthesis. Um, this paper, for example, here they put and then um, PMMA polymer they put and then irradiate with argon plasma, and then you can find this GNR gradual etching of this multi-wall carbon nanotube. But this arc discharge, this is for the CN Rao's group in 2009. They also synthesized through arc discharge graphene with boron and nitrogen when the electrical discharge is formed in the presence of diboron and pyridine respectively. The dangling bonds on edge carbon atoms become fantastic mechanical properties, as I just showed, bendable, stretchable film, high charge carrier density. If you put an electric field, BN, the inorganic analogs have been prepared, like BN, BCN, MOS2, WS2, etc. analogs. Room temperature quantum Hall effect was observed by these two Nobel laureates. Flexible touchscreen, just now I showed. High TC superconductivity has been out. If you can make 4% whole doping in graphene, you can get high TC superconductors. Up to now, 2% has been achieved. The TC is quite high, close to 90 Kelvin. Metal-free magnetism, because there are some carbons which are unsaturated carbons can show magnetic behavior, and gas storage because a lot of surface area is there. Okay, and many more things. This does not, space is not allowed. Space is not much here. And okay, so thank you so much. This is my group in 2009, 2011 group, and the current group. These many people. I thank them for working on many of these things. And thank you for listening to me.
Thank you, sir.
Okay, so let me tell you, I will come to this one which I was asking. Yeah. So let me ask all of you. As you can see, do you have any question first of all?
Okay, thank you, Professor Swapanpati.
Thank you.
I'm Dr. Sanjeev Bhattacharya here, Associate Professor, UGC HRDC, North Bengal University. I'm the internal coordinator of this program.
Okay, no, one second. There is a question.
Sure, sir. Thank you, sir, for your nice presentation. This is the time for question answer session. So I would like to request our teacher participant to ask valuable question to Professor.
No, there was a question in the somebody had written
Chat box, in the chat box.
In the chat that you said inert gases are not inert anymore. Why? I'm curious to know how they interact with other elements nowadays. No, there have been, long back, XCF4 have been produced. Xenon fluoride, XCF2, XCF4, many compounds have been formed by the xenon, and argon compounds also are there. So they are not inert anymore, actually. But the bonding is very interesting, by the way. One could give a talk on those things. All right. Yeah.
Okay, thank you, sir.
Sir, can I ask one question?
Sure.
Okay. Sir, actually, you have shown in your presentation, I have observed a few of your slides that regarding the electrical measurement or electrical conductivity related issue, 2 probe and 4 probe. There is a debate, highly conductive, highly resistive, that is dielectric material. Usually, 2 probe methods have been used. Actually, in my laboratory, I have done this setup. Sometimes 4 probe is better for electronic contribution. So thing is that 2 probe and 4 probe, actually, if the system is full of mixed conductors, like electron and proton, both are there. Okay, polaron. You have mentioned polaron and ion both are there. In some conductor, mixed conductor, how to segregate the ionic conductivity and polaronic conductivity? Is there any standard methodology?
Yeah. Let me tell you, there are quite a few measurements you can do. One is 2 probe, 4 probe. 4 probe one should use every time, because you'll have flexibility of defining which is gate, which is source and drain.
Right.
You can change it because 4 of them are there. Okay. 1, 2, 1, 3, 1, 2, 4, like that you can use. Okay.
So 4 probe means 2 probe for sending current and another 2 probe for measuring voltage.
Exactly. Okay. So the more flexibility will be there for you to change this source and source drain and which one are you putting at what. Okay. 4 probe is much better.
Much better.
Then second thing is you should do time of flight measurement for mobility.
Okay.
In general, if you go through this long chain direction, there is electron flow. Okay.
Right.
So it is very difficult to get how much is the hole, how much is the electron mobility,
Right.
except from this time of flight.
Right.
you know that these are all carbon systems, sp2 carbon. There are pi electrons are there. Okay, and so along that one, it will be mainly electron mobility.
Right.
Perpendicular one will be the hole mobility. Or you can get through conductivity, from there you can get the mobility, but you will get total mobility, electron and hole. You cannot get separately.
Right.
Or one can do Hall measurements, from there again Hall conductivity, from there you can get electron and hole mobility, but not accurately. So there are problems to get electron hole mobility. The point is, one should take help of theory also. If somebody predicts the electron hole mobility this much, and then if your measurement is done, then you can say that, oh, this is comes from the electron basically, not from the hole. Yeah.
Sir, do you have this facility in your laboratory, time of flight
Not
measurement?
I do not do. I am a theorist. But
Okay.
our people like K.S. Narayan, Professor K.S.
Okay.
Narayan,
Okay. Okay.
he
Okay.
does time of flight.
Okay. So I will contact you later regarding this issue.
Yeah.
Sir, I have a question.
Mhm.
Sir, you have mentioned the solitonic nature. Sir, soliton is propagated through a pulse or wave-like nature. But where have you introduced here?
I did not introduce that way. See, for example, solitons, what this polyacetylene, when they were observing, they found that in the middle of this absorption curve, when they're doping, you are getting a peak. Okay. For example, 1.4 was the gap in polyacetylene, but around 0.7 electron volt, they were finding a middle, the peak, and that peak, depending on the doping, it was they thought this is a solitonic peak. Okay. However, now things have changed. There is no solitons anymore. It's all exciton, electron hole pair. You get trions and other things also. Those are advanced stuff. But the point is, the solitons are seen in ferromagnets. Ferromagnets, you have domain structures, and for example, you think about iron. Iron is a ferromagnet. Okay, in room temperature, it's a ferromagnet. But because of the dipolar interaction, to save the dipole energy, it breaks up into upspin domain, downspin domain, and various types of domains. Okay, and upspin domain, the volume is same as the downspin domain volume, and that's why it becomes zero. The magnetization becomes zero. And if you are heating the things, basically one of the domain at the expense of one of the domain, other domain is growing. So you get some magnetization, because of which it attracts, it shows ferromagnetic behavior. It attracts the pin or something. However, with time, that extra one again goes back to the original one, back to this one. This motion, this how the domain in fact flips, is a coherent, incoherent, or how does it go? In fact, you can see that one when you do this hysteresis plot. Hysteresis plot, first you plot with magnetic field. When you draw the initial part, you try to analyze that one, you will find some noise actually. And those noise basically data for the T1, T2 of the domain motion. Okay. In fact, the solitons, etc., is a tan hyperbolic function. It's
Okay, sir. Nice, sir.
Yeah. Any other?
Any other question from the audience?
Sir, you talk about Samsung company nowadays using 30-inch graphene electrode sheet.
Yeah.
Is it also behave like a liquid crystal also?
No, liquid crystal is different. No, it's not
Yes,
liquid
sir.
crystal. Actually, it's a flexible electrode. Roll to roll flexible. Touch screen. It's
Touch
a
screen.
beautiful touch screen as well as flexible.
Okay.
Amazing. This graphene material is an amazing one. Only thing is that it is not a metallic one. That's the whole problem.
Yes, sir. Yes, sir.
But if you dope it again, it will not remain the same material, na? Or
Exactly, sir.
like a covalent bond with something else, it's no more the same material.
Yes, sir. Its various properties yet to mimic, so that
Yeah,
many
yeah.
application
Yeah.
Are yet to come also.
Yeah, and there are many companies now, Indian companies also, they are making this graphene as a huge amount of graphene, kilogram of graphene.
Yes, sir.
It's a good thing. They're proceeding to a nice way, you know. Uh, yeah, but then experimental advancement also should occur.
Exactly, sir.
For example, mobility. This mobility, electron hole mobility in conjugated polymers. Most of the organic conjugated polymers, they have hole mobility is quite high, but electron mobility is pathetic actually. That depends on something called reorganization energy. This Marcus reorganization energy. That is, when you put a charge, how much is the change in structure, and because of that, how much energy change occur. You put an electron to a conjugated system, the structural change is huge. Okay, but if you put a hole, structural change is not much, because they are electron dense, pi electron dense organic systems, conjugated systems. Because of that, the electron mobility is very, very low, but hole mobility is very large. But when you come to graphene, the electron mobility, by the way, this mobility, for example, silicon, amorphous silicon, it is 10 to the power 3 orders electron mobility, centimeter square per volt per second. Okay, but if you go to organic polymers, it is 0.01. Okay, 10 to the minus 2, which we use semiconductor for FET and other things. The amorphous silicon is 10 to the power 2. But if
Yes,
you go to
yes.
graphene, it becomes 10 to the power 6 actually, graphene. But it is not a metal. So people have been trying, for example, MOS2, which has a electron mobility of the 10 to the power 6 order actually. MOS2, electron and hole mobility. So people are trying to do this, do these things. There are and one should put some strain which increases the mobility. Strain along one direction or biaxial strain. So one should do some engineering and make the structure.
Yes, sir. Its tensile strength is also an important.
Tensile strength also can increase, exactly. Yes.
Sir, another different question between allyl cation and allyl anion, CH2 double bond CH single bond CH2 minus or plus. Which one should be more stable?
Cation will be more stable.
Sir, because in anion, the extra electron in the anti-bonding molecular orbital.
Exactly.
Sir, it's a common question, generally comes in our undergraduate syllabus.
Yes. Because of the anti-bonding molecular, they are in positive energy, that destabilizing energy. By the way, one more thing, let me tell you, this concept of bonding molecular orbital. It was in Linus Pauling in 1950. He had suggested that sharing of electron. The electrons come closer, and both are negatively charged. So there will be huge repulsion. But every bond is stable due to kinetic stabilization. That means this hydrogen molecule, interesting, hydrogen is having a Bohr radius of 0.52 or angstrom, okay, 0.5 angstrom. But hydrogen molecule interatomic distance is 0.76 or 78 angstrom. I forgot how much, but it is like that.
Yes.
It is not a hard sphere model. It is soft sphere. That means it enters inside. Okay, there is an internuclear region is much dense with electron density. That's because electron 1 in hydrogen 1 gets more phase space to move around. Similarly, electron 2 in hydrogen 2 get more phase space to move around. The amount of kinetic stabilization the electron gets, that overwhelms the repulsion that it has to face because of staying together. So every covalent bond is due to kinetic stabilization, not because of electron interaction, not potential energy, but kinetic energy.
Yes, sir. Sir, in some book also, this explanation is given through alpha beta parameter also.
Yeah. Alpha beta. Alpha is the site energy, every atomic energy, and beta is the resonance energy or coupling energy.
Exactly, sir.
That is negative generally.
Thank you, sir.
Hello.
Yes.
Regarding this allyl cation, just want to know one thing. How about the stability of benzyl cation and allyl cation?
Well, benzyl cation will be more stable than allyl cation because a ring system.
Hmm.
See, interestingly, if you see a ring system, because it's a periodic system, okay,
Hmm.
and there is a ring current which is produced. That means electron is moving leftwise, otherwise rightwise, okay,
Hmm.
but both are not cancelled out because of
Hmm.
interaction. There is a net current
Hmm.
which flows because of which you see NMR chemical shift of those hydrogens, right?
Hmm.
Benzene hydrogens have chemical shift different from the other hydrogens because of
Hmm.
this current, ring current or
Okay.
persistent current which is there. The
Hmm.
point is because the ring structure you have double degeneracy.
Okay.
Okay, bonding you'll have two guys are there, so you can put 4 electrons.
Hmm.
But if you have a chain structure, then you have single guys, non-degenerate single guys. So there are
Hmm.
more antibonding molecular orbitals.
Hmm.
Because of the ring, it gets extra stability, and that is the
Okay.
resonance energy. Yeah.
Hmm. Okay.
Benzyl anion should be less stable than benzyl cation for the same reason.
Exactly.
Benzyl anion.
One more query regarding that staggered and eclipsed conformation. You have shown the ethane molecule. So if we replace one hydrogen in each methyl group, so it's FCH2 CH2F. So how we will explain the conformation of that molecule, the
Of course,
stability
conformation
of
will be
the
staggered will be more stable, but I want us to find out how much stable. This CH3 is 3 kcal per mole.
yeah. In case of CH3 it's staggered, but in case of
to
FCH2
F.
CH2F, eclipse is more stable.
Is it? Okay. Oh,
Yes,
because
if
of
I'm not wrong.
hydrogen bonding.
So
Proving the negative ion is there.
hydrogen bond between
FH and CHF.
CFH. Okay. So
I think is it eclipsed or Gauss conformation? I'm not sure. Is it eclipsed conformation stable?
I think Gauss.
Yeah.
Gauss.
Gauss, exactly.
Not eclipse. I was wrong. Yeah, Gauss.
I was guessing that one. Yeah.
Mm. Okay.
Okay.
So
Thank you. Yes.
I am inviting you, Sohunda, here in our campus for the cricket match.
How can I come now?
Upcoming tournament in next month.
No. I remember I played there a little bit last time I
Yes.
was there.
So come next month. We have tournament. I will inform Anirbandha.
Anirbandha is here.
No, I'm not in the department. I am just out of the department now. So I will inform him.
Okay.
Okay, thank you, Professor Swapanpati, for your nice and informative presentation.
Thank
And
you
you
so
have
much.
taken many more questions from the audience. Thank you, sir, once again. And we expect you as a resource person in our future program also. So
Sure.
here our course coordinator, Dr. Sajal Das is also here.
Oh, Sajal. So, no, in fact, he only sent me the things in the middle of the night, actually.
Yes.
But thank you so much. Okay. Certainly, I would like to visit the place. And many people I know of there. I was there in Tokaryasala. That Vishwas.
Yes, Bhaskar.
Bhaskar had organized.
Okay. Thank you, sir, once again. Thank you. Let's end our session here.
Yeah.
Let's end our session here. Okay, dear participants, this is the time for lunch break. So
Yes.
we have short lunch break today. You should join over here by 2 p.m. sharp, okay? Because our value
Okay, sir.
program will start from 2 onwards. Okay?
Okay.
Thank you.
Okay.
all.
Okay, thank you so much.
Thank you.
All of you,
Thank
take
you, sir.
care.
Thank
Stay
you,
well.
sir.
All the best.
Thank you, sir.
Thank you.
Thank you, sir.
Thank
We
you,
will
sir.
start our military program from 2
Thank you,
onwards.
sir.
Okay, so you should join by 2.
Thank you, sir.
Okay, sir.
Okay, sir.
So much. I'm leaving now. Okay, thank you.